Hello everybody, this is Mr. McAllen again, and what I want to talk about tonight is I want to talk about the power series, and this is an introduction to a power series so that we can understand how this would apply when we're dealing with using series to approximate functions. So what we're going to first do is talk about what an infinite series is. We're going to talk about what a geometric series is. You should have had this somewhere in pre-calculus, and our goal is to, with the geometric series, is to construct a representation of a function using that series, and to adapt the series to make new connections to other types of functions. So let's first start out and just define a few terms. For instance, an infinite series is a series of terms that, when you add them up, you have an infinite number of terms, and they would add up to a number of n terms, or well, this is the nth term, but as you can see here, it's going to continue on forever, or you can just simply represent it using the sigma notation, where we say that we start at the first term and we're going to go to an infinite number and of the kth term. So this sigma notation is simply a shorthand notation to represent all of these terms all added up. With that being said, let's discuss the idea of convergence or divergence. For example, if let's say that I was going to sum up the number 1 and do that for an infinite number of terms, it would be clear that the sum would go to infinity, and that would be a divergent series, because it's not going to a fixed finite amount. Another example of a divergent series would be something that looks like this, where we say we're going to start at 1, we'll go to an infinite number of terms, and we'll have -1 to the k power. And when we start to expand the series, our first term would be -1, our next term would be 1, our next term would be -1, and so on. And because the series is alternating between adding 1 and -1, our summation will always be between -1 and 0, and -1 and 0, never reaching a fixed finite value. You can see here when we add up these two terms, we get 0, we add up this, we get -1, we add this, we're back to 0, we add this, we're at -1. This is another case of a divergent series. So when does a series converge? Well, we happen to study in pre-calculus geometric series. A geometric series is one where, for example, if I represent the repeating decimal as 3/10 plus 3/100 plus 3/1000 plus so on, I have basically a geometric series where my first term is equal to 3/10, and my R value, which is my geometric ratio, is 1/10 for every term thereafter. So what happens is if my R value in a geometric series is between 1 and -1, or in other words, you could say the absolute value of the ratio is less than 1, then this guarantees convergence. And what we'll see is, we had this formula in pre-calculus that said the sum of an infinite number of terms is equal to my first term divided by 1 minus my geometric ratio, as long as the ratio was less than 1. So what happens is we can look at this, and my infinite sum for this will be 3/10 divided by 1 minus the ratio, which was 1/10. And when I look at this, I have 3/10 times, when you divide by a fraction, the fraction here, is 9 over 10. You multiply by the reciprocal, 10 over 9, and this summation will equal 3 over 9, or 1/3. And that's what we said that that decimal we had before, the repeating decimal of 1/3 was that we started. So to some, this may look like kind of an engineered case for a geometric series, because I started out with this. I broke this up into sum of infinite number of terms. I used my geometric infinite summation. I had the condition that r has got to be less than 1. And I showed that with the formula that we had for an infinite sum, that we actually come back to what we started with, 0.3 repeating. Well, let me show you a pictorial diagram that shows the same representation to prove that the geometric series converges. Here we have a box or a square, and we know the area is equal to 1. Well, I'm going to consider adding up a half as my first term, and then I'm going to divide this in half, and that's really a quarter. And then I'm going to add the next term, and that's an eighth. And then I'm going to add the next term, and that's a 16th. And as you look at the progression of this series, you could say to yourself that this is a geometric series. How do you know that? Well, there's a ratio between the terms. The r value is equal to 1/2. Between each term, the term following it is 1/2 of the term it was before. So this fits the build of my geometric series, and if I add up my infinite sum, if I were to drive this this problem here and keep dividing it for all eternity, the sum would be equal to my first term divided by 1 minus my geometric ratio. So the infinite number of summations would be 1/2, because that was the first term, divided by 1 minus 1/2, which is 1/2 divided by 1/2, which again is equal to the area that we said we had before of 1. One other thing we should mention about this formula is if the r value is greater than 1, then the summation would diverge, meaning it wouldn't converge to a fixed finite value. Let's for a moment just reconstruct or rewrite the geometric series. And we'll just say for the time being that the geometric series is we have a plus a times r plus a times r squared plus a times r cubed dot dot dot. We would have a times r to the n minus 1 plus dot dot dot, meaning it continues on, and our summation, we can write this in sigma notation. If we start out at n equals 1 and we go to an infinite number of terms, then we would have a r to the n minus 1. Now what we're going to do at this point, since we've already discussed the topics that we covered in this short video, was we discussed divergence versus convergence, what a series is, or an infinite series, and we discussed some examples of geometric series. In the next video, what I intend to go over is how we can work with a geometric series that actually models a function that we know. And this is actually the first way that we experience a Taylor polynomial. So check YouTube for that video, and that would be the second part of this lesson.